So, good morning. Hello. Hi. Here's the homework. So the homework results are very good. Otherwise, this matters to the test. So I will give you the complete solution so that you can fix any problem if there was a problem. So again, this matters to our next test, and it may matter to the final, so it is really good to know about it. And just a general remark, when you address problems, take the time to ask first whether your approach is definitely correct. It is obviously a main disaster to apply any approach to something that is not made for this approach. So here it is about specifying the equation, and what you can expect is some sort of modification when it comes to the test. So it is about matching the problem that we have and the framework that we discussed. So the Sturm-Liouville and the Fredholm alternative. And then it is, when it comes to a problem like this, pretty much about the understanding of the lambda. And there is one kind of problem lambda, which is 2 in our case. And independent of that, there is the eigenvalue lambda, which is defined by y double prime plus lambda y equals 0. So I followed usual notation here. We can write it like this, but it needs understanding that there are 2 different lambda involved. One is independent of the problem lambda. So when I talk about the problem lambda, I have 2 in mind. Yeah? And this lambda could be equal to one of the eigen values. So it could be pi squared. And then you have to ask again which sort of solution you can get. Yeah? So that are 2 very different things, the problem setup and the eigenvalue defined by the equation structure. And otherwise, we follow our usual strategy. What we do is to ask what are the eigenvalues, eigenfunctions of our problem. And then it is different in this case, but it is the same strategy as looking at PDE and expanding the solution in terms of eigenfunctions and using some sort of adjustable coefficient like un and getting an ODE for un. Here it is not an ODE for un, it is a simple algebraic relation given by Bn equals Cn over lambda n minus 2. So here you can see the difference between the 2 lambda values. Lambda n obviously is the eigenvalue of the function, and 2 is the problem lambda. And if they are different, then everything is good. So this is one major thing related to the understanding of such problems. One other thing is to follow the formalism that we developed, meaning that it needs to correctly identify the Ly. And here it turns out that the f is equal to x. I try to indicate this, that one should consider which sign is a correct sign. Otherwise, if there was any problem, I took off a half point and you got it back with a bonus point. Yeah? So you should be aware of this philosophy, and in particular the difference between the problem lambda and the eigenvalue. And then everything works. When it comes to the test, there will be no trick. I do not try to trick you. So it will be a problem like this, yeah? And you should simply follow the formalism. Otherwise, my understanding was that almost everybody was doing very well. And when there was any problem, then it was about integration and, let's say, a factor of square root of 2 when it comes to the Cn and combining the Cn with the eigenfunction. So square root of 2 squared makes 2, yeah? Excuse me,
so for 1c, I left out that square root 2. Why?
Where are you?
For 1c for the cn.
1c, yeah. Hmm?
So it's a square root 2. So I left out that part. I'm wondering, like, what's the idea behind putting it there?
You did not involve the square root of 2. So it comes with a normalization of the eigenfunctions. Yeah, the hn is square root of 2 times sine. So this is also something that is kind of particular in this case. Okay. Usually we are good with finding sine and cosine functions and eigenvalues. But here we have to explicitly honor this condition. And usually there's also an r involved, but it is 1 here. So that integral over hn squared should be equal to 1. Yeah, so there was no problem. Again, my understanding was that almost everybody had a perfect understanding of how to do this. And if there was a problem, then it was the minus sign or square root of 2 something. So not any thing that is really serious. Otherwise, regarding the... You want to say something?
Yeah, we have a question on number 1 also. You wrote that Bn is Cn over lambda n minus 2. Then in the solution, should that be a minus 2 in the denominator rather than a minus 1?
Oh, thank you so much.
No problem.
Thank you. I'm tired. So, yeah, sure, that should be true. So otherwise, is there any question about this? You will see this on the test, most likely. So, and you will also see the second problem, most likely. And my understanding, actually, I think I saw always correct results. Maybe in one case I saw instead of a 4, a 2 or something. Otherwise, everybody knows how to deal with it. It's a nice problem, actually. So it is certainly doable. And what it takes is to correctly set up the Euler-Lagrange equation, and probably just to double check the solution. So it is usually very efficient to just ask whether the solution satisfies the boundary conditions. And if there's a problem, then we can often see it in this way. So any question about doing this? Very good. I have a problem with the timing, with the test. So what I will do is to continue today with the final preparation. So I will continue to present all that, including relationships between approaches, things like this, regarding the first part of the semester. Then to have you fully prepared for the test on Monday, I will switch to methods of applied 2. This is about that what we just saw here in homework. Then you have the graded homework in your hands. You have the summary, so you know what you have to expect. And I will also tell you again which sort of 3 problems you can expect. So there will be no surprise. And then I will switch back to that what is left with regard to the first part. The alternative would be to rush through the first part to finish it. I don't think it is a perfect idea. I think it is better for you when you have the complete picture and time to think about it and to ask any questions. Is this confusing? Very good. Then I will continue today with that, and on Friday I will switch to the test preparation and finish actually the second part of the semester, and then I will switch back and finish that what is left here. So So I talked about methods for first order equations, and then we switched to methods for second order equations. This is just to remind you about the structure of that what we did. So we look at the unbounded case. Again, when you look at an equation, your first thought should be about the domain. This decides about everything. And here we have the case that we have only positive x values, and the way to deal with that is to work with reflection. So I will try here to indicate in green which methodology is applied, and then I show you again what we have. So with respect to the wave equation, we did the following. So we used here the idea of odd functions. And the idea is pretty simple. The solution is only about positive x values, so we can do whatever we want with negative x values, so with a function for negative x values. And we extend it here to the case for which we have a solution, and it reads like this. I think regarding our first test, there were a few questions about doing this. Um, so you can use your notes, okay? You can use whatever you want actually, except your iPhone's internet. Okay. So this is about plugging in the data that you have, yeah. And I think in one case there was a question mark of how to work with these arguments, and the meaning is obviously when we have f and g of x, then we use these functions at the corresponding arguments. Yeah? Is there anything that is not fully clear about it? Okay. Is this a Green's function writing? No, it is not. Is it possible to have a Green's function writing? Yes. Do you want to see it? No. So, for the second case, it is pretty similar. Bless you. So obviously this is a Green's function representation. So we run directly into this writing. Note the integration bounds, which matters, otherwise it is pretty simple. Here too, it just needs to plug in what we have. So you can come with your tables, whatever you like. Yeah? So to know about integrals, that is not the point here. The point is to make a flexible use of methodology to get things done. So we move on.
Is this a diffusion equation or the wave equation?
Yeah, thanks. Wait a second. That is a wave equation. Thanks.
I have a question. Maybe I'm crazy here, but should we have an initial condition as opposed to only boundary conditions?
So we have here initial additions for u and ut at t is equal to 0.
Should I not have one where x is equal to 0 and t is equal to t, I guess, like u of, or do I not need that here?
This is the infinite space.
Oh, okay.
Yeah. So 2.3D, yeah, infinite space. So we talked about Kirchhoff's solution, and we talked about the two readings of this solution. And in one of the homework problems, it made a difference of which sort of solution you use. So depending on the structure of f and g, it can be more important, it can be more appropriate to use, let's say, the delta function writing or the writing including the surface integral. So it just depends. One comment that is definitely relevant, at least to the final, is the following. So if there is wording about radially symmetric solutions, and when you are not sure about it, you can definitely ask me. It is way easier to work with these forms for the solution compared to using Kirchhoff's solution. You can try to use Kirchhoff, but usually it is way, way harder. And this was also one of the homework problems. And the idea is to specify the solution structure for the initial conditions. So we take u at t is equal to 0 equals f, and ut at t is equal to 0 equal to g. We run into two equations to solve for f and g depending on r. If we have this problem, then we just have the r, and you would see it in the writing that f and g, the only f and g are only functions of r. Then we use these equations to solve for f and g as being functions of r. And the point is then to replace the r by the argument that we need. So we use f and g at r by replacing the r by r plus ct and r minus ct in our solution. Is this good with you? Okay. So this is actually not too difficult. Two things. The 3D translates to 3 over 2. So each dimension, you see it here, is n, makes an n over 2. And the k is usually written at x and t, and we use it then at x minus y and at. Okay? Yeah?
Should it be a vector of x squared, or is it the norm of x squared? Or is it the norm of x? Sorry, like e to the power?
This is x1 squared plus x2 squared plus x3 squared. I can get rid of this, right? You saw the B part for the diffusion equation. We talked about the solution, but you did not see the Green's function representation for the wave equation. The idea is simply to solve the problem as we did and to plug in the explicit expressions for the coefficients considered, and then to reorganize the solution to get an integral over the domain considered times a Green's function and its derivative. So this is the usual structure for these problems, that we have G and its derivative for the wave equation. Please have in mind this applies to the simplest possible case, to the homogeneous PDE, homogeneous boundary condition. What I will do is to provide the second block on Friday so that you are prepared for the test. And after that, I will finish the discussion of second order methods, including, for example, the question of how to shift the data, so to deal with more challenging cases. Okay, have a good time. See you next time.